definition of this. So in the school, do you recall the definition of this term, Samir?
It is an opposing force, right? Which is because of contact.
Yes. So is this the definition?
Yeah.
Okay, so this is actually an incomplete or rather incorrect definition. Friction does not oppose, not necessarily opposes the motion. The correct definition of this is this: friction is a force that opposes the relative motion. Now we will understand what do we mean by this term using an example. Okay, so let's say you have a block of some mass m placed on the ground, right? And if you apply a force on it towards the right hand side, now because the ground is having friction, so there will be a friction acting on the block towards the left hand side. Now it appears that friction here is opposing the motion, which should mean that the definition 1 is correct. But let's try to understand by one more example. Let's say if you have the same block kept on top of another block, and this system is placed on the ground. In this case, the applied force F is being put on the bottom block and not the top one. Now if I draw the free body diagram for the both of these individual blocks, let's see what happens. So if I consider the bottom block, which is having mass m, so it will have a weight acting downwards and a normal reaction acting upwards, and a right force of capital F. Now because this bottom block is in contact with the surface, so it will experience a frictional force, let's say F1, acting towards the left, right? Now consider that the surface, this particular surface, so the surface on which the smaller block is being placed, that is also rough, which means it also has a friction. Now can you tell me in the free body diagram, since the surface is rough, so definitely the bottom block will experience some sort of friction. In which direction that friction will be, to the left or to the right?
Left.
Okay, so can you tell me the reason? All the answer
So the
is right.
force is applied towards the right, so the friction will act in the opposite direction.
Yes, true, but one way to look at it is, consider this. Okay, so this bottom block actually wants to move to the right, but the top block is giving a resistive kind of force to it. So the bottom block wants to move towards the right, but the top block gives it a frictional force which opposes its motion. That will be F2, let's say. Now F1 and F2 could be the same, could be the different, depending on the values of friction. Now let's consider the topmost block. So in this particular case, there is no horizontal force. This capital F was being applied on the bottom and not the top one. So in the top block, that capital F won't come. So can you tell me any of the what forces are being acted upon the top block?
mg.
Oh, Smira, you joined. So when did you join?
So like when you were discussing the definition.
Okay, so all right. So basically what I'm trying to explain is the first definition is incorrect. The right definition is a force that opposes the relative motion. Now to explain this, I'm telling you an example.
Yes, sir.
Okay, now Smira, mg is fine. Is there any horizontal force acting on this block, the top block?
The horizontal force that is applied on the lower block, that also has an effect on the top block.
Yes, absolutely, it has an effect. See, if you look at this whole figure while sitting on the ground, you will see both the blocks are moving to the right. But if I draw the free body diagram of the top block individually, this capital F, you would not write capital F for the top block, but there is a force which is responsible for the forward motion of the top block. Can you figure that out? What is that force? See, basically what is happening, consider the bottom block only. The bottom
I
block.
think it's the frictional force that is pulling the block towards the right.
Yeah.
Yes, and okay, let me say this is it. So what will be this value of the friction?
F.
F.
No, not F. No, not F. F2.
Absolutely, this is F2. This is because the forces will follow the Newton's third law. Every force has an equal and opposite reaction. So
So just to clarify,
mhm,
F1 is the force that is between the lower block and the ground,
ground.
and F2 is the force between the top block and the lower block.
Yes, absolutely.
Okay.
Now, in reality, see, forces occur always in pairs. So one might ask, where is the second F1? Could you tell me where is that friction? Where is that pair of F1? I mean the opposite.
That is F.
But
Capital F.
where can we show that? No, no, that is not capital F. See, F2 has a same F2 towards the. I mean F2. You can see F2s to the left and to the right, but you only see F1 to the left. Where is the F1 to the right? See, this is Newton's third law, which states that these equal and opposite forces act on different objects. So you can see this F2, this particular F2 is acting on the bottom block, and this F2 is acting on the top block, so acting on different objects. So let us say if I draw the free body diagram of the ground itself, so then this F1 will come here, so at this point acting towards the right. Are you getting it?
Yeah.
Right, so generally we do not draw the free body diagram of the ground, but this is just for explanation's sake that forces occur in opposite pairs and they act on different objects. Now just consider this, the top block. For the top block, friction is actually responsible for its motion, right? So can you observe this, that friction is the force which is pushing it towards the right, isn't it?
Yes, sir.
This means
Yeah.
this particular definition, which is the first, that is incorrect. A friction does not oppose the motion, it opposes the relative motion, and in some cases it actually aids the motion, right? So please write this down, and then we go to the next.
Done, sir.
Okay, Smera, done?
Yes, sir.
Okay, now let's move on. Okay, now this is to discuss the two types of friction. So friction has two basic types, and one is called the static, and then we have the dynamic friction. Now let's go through the definition of it. So read this. So when two bodies do not slip over each other, but they have a tendency to do so, the friction involved in this case is static, and when the two bodies are actually moving, so they are slipping over each other, in that case the friction is called the dynamic friction. Now let's try to understand this by again taking examples. What do we mean by this? They are not slipping, but they have a tendency to do so. Okay, so let's consider case by case. This is a block kept on the ground. Let's say the applied force is 0, so there is no applied force, consequently there will be no friction. There is no need of friction. Right, so this is the first example, the most obvious. Now let's see the second. Now the same block and 3 different cases. Now in this particular case, let me give you a value. Let's say the maximum friction which this ground can provide, the ground on which the block is placed. Hypothetically, let me give you an example. Let's say this is 50 newtons. So 50 newtons is the maximum frictional force that can exist. Now let's say if I put a if I apply a force of 10 newtons. Now although the maximum possible friction is 50, the friction in this case will not be 50, isn't it? Can you tell me, Saumil or Smera, what will be the value of friction in this case?
It will be 10.
Yes. See, since the maximum maximum possible friction is 50 newtons, so till the time the applied force becomes 50, this block will not move, and till that time the frictional force is equal to the applied force, and that is equal to 10 newtons. So the velocity of this object is 0, or we say acceleration is 0. Now let's take another example. If I take capital F as, let's say, 30 newtons, in that case the friction value becomes 30, so it increases from 10 to 30. Let me even increase the value of the applied force further. Let's say it is 40, then the friction force again increases to 40. So now as you can see that as the force is being applied, the value of the friction is increasing, right? So it continuously increases till it reaches the 50 Newton mark. Now the catch is, in this particular case, now both these bodies are not moving, so they are not actually slipping. So let me give you the definition of this. Okay, so this friction, which is equal in magnitude and opposite in direction to the applied force, this is what we call the static friction. Static because the body is at rest, right? So that's why we say that static friction is actually a self-adjusting force. It keeps on increasing depending on the applied force. Okay, so please make notes for this, and then we continue.
So that statement which is written here, it is equal in magnitude and opposite in direction.
Mm-hmm.
That is for the static friction, or that is only for these three examples?
That is for static friction. So if the force, let's say, goes from 0 all the way to 50 newtons, so the friction applied in all of these cases is static.
So beyond that, it won't be static
No,
anymore.
it won't be static.
It
So
will be dynamic.
yes.
I'm done writing, sir.
Okay. What about you, Smela?
Yes, sir.
Okay. Now let's move on. Okay. So in this figure, you have seen that as we are increasing the force, friction also increases. In this case, we had assumed that the friction maximum value is 50 newtons. Now consider a case when the applied force actually becomes equal to that maximum applied force. So what will happen, that the static friction, let's say this is represented by the symbol Fs, static friction. So the static friction increases as the applied force is increasing. Now let's say if the capital F becomes 50, so that will mean we have reached the maximum value of the static friction, and that is what we call the limiting friction. So limiting friction basically means the maximum value of the static friction up to which the body does not move. So in this case, if the applied force is 50 newtons, so the friction applied in this case will also be 50, and this is the maximum possible value. So which means we can write it like this. So a static friction, which is represented like this, its maximum value is called the limiting friction, right? Limiting friction is represented by this F and L. Now experimentally it has been seen that this FL, or the limiting friction, is directly proportional to the normal reaction. So if we see the free body diagram, in this case it is easy. So mg pointing downwards and the normal reaction is upwards. So in this case normal reaction is actually mg. In this particular case only n is equal to mg. In different cases it could be something else as well. So okay, so no need to actually write this, no need. So just write this, FL is equal to mu times the normal reaction, where this is mu s. Now mu s is a constant which is called the coefficient of static friction. So let me repeat with what each term means. FL stands for the limiting friction, n is the normal reaction, and mu s stands for the coefficient of static friction. Now this is a dimensionless constant. Just if we consider just this particular example where normal reaction is mg, so for this case FL would be equal to mu s times mg, and this is the maximum value of the static friction. So write this down.
So I'm still a bit confused about this limiting friction.
Okay, all right, so let me repeat one more time. So
So like what we had done in school, like it was something like the friction on the body is equal to nu into n.
yes,
So like why have we written FL is equal to nu into n? Just because it is static. Like this is for static, that's why, right?
could you repeat, in your school what have you done?
Friction is equal to nu into n.
That is correct.
Yeah, that is correct, but like here we have written limiting friction instead of friction.
Okay, so let me explain that. See, friction is equal to mu times n. So see, in the questions the n is constant because it depends on the weight. Mu is also a constant, which means the value of friction will be constant, right?
Yeah,
This completely goes against the principle that static friction is a self-adjusting force. It will start from 0, it will keep on increasing as the applied force is increased, and when it reaches the maximum possible value, that is what we call this limiting friction. And the formula which you are saying, mu times n, this is for the maximum value of static friction. Are you getting it now?
yeah. This is not like a general formula that we wrote, but this is the general equation that we had used in questions.
That is fine, but that is not entirely true. This value is only for the maximum possible value of static friction. So as we just saw, the friction value increased from 0, 10, 20, 40 all the way up to 50. So isn't it increasing? It is not constant, right? So this formula is not valid then. So the logic is that this formula is only for the maximum possible value of the static friction, and static means the body is at rest. This means even though the applied force is 50 newtons, the body is still not moving. So this is the key. The body does not move and the friction has its maximum possible value.
So
In
what is
case
the
of
value
like,
of mu?
Pardon, Smera?
So what is the value of mu?
Mu is actually a constant whose value is less than 1. So it will be in decimals. It will be given to you in the question.
Okay.
Okay. Oh, so
so
I
like
got
you
it.
said,
So
for the f is equal to nu n, the nu and n both are constant. But when we look at fl is equal to nu s into n, isn't that value also a constant?
yes, it is. It is a constant.
Okay, got it.
Okay,
So I'll
Smera.
need 2 minutes. I haven't written
No,
this
no
down.
problem. Smera, you had asked me the value of mu s. So mu s here is not a universal constant. This, see, the value of mu actually depends on the surface, on the contact surface. So that value will be given to you in the question, and this value is always less than 1.
Okay.
Done, sir.
Okay. Smera, let me know when you are done.
Yes, sir, done.
Okay, great. Now, okay, so in this particular case, we saw that the applied force reached the maximum possible value of friction, which was 50 newtons. Now let's increase the force even further. Let's say it is 60 newtons. In that case, the body actually starts to move, and the friction in that case is what we call this. This is the kinetic or the sliding friction. This means the body is actually moving, so body in motion. Now please pay attention here, this is critical. So if the applied force was 50 newtons, the friction applied was static and its maximum value was 50. So it is at rest. Let's say if I increase the force even further, which is 60, now in that case the friction which is being applied, that is what we call Fk, or the kinetic or the sliding friction. Now the key here is this kinetic friction, and this is the limiting friction actually. So the value of kinetic friction is less than the value of the limiting friction. So this value of Fk will be actually less than 50. So this is actually found experimentally, that Fk value is always less than Fl. So it is possible that this Fk could be 45. It could be any value less than 50. That will be given to you in the question. Now earlier we had seen that the limiting friction is equal to mu s times the normal reaction, where mu s is the coefficient of static friction. Fk follows the same rule or formula. Fk is given by this formula, mu k times the normal reaction, where mu k is called the coefficient of the kinetic friction, also called the sliding friction. The only difference is now the body is actually moving. Now if I compare this inequality using this, we can see that mu k value is always less than mu s. This is always true, but either of these two mu will be less than 1. So did you understand this? Any doubts? Somil?
Understood, sir.
Okay, so please write this down.
Done, sir.
Okay. Smera, let me know whenever you finish.
Yes, sir, done.
Done? Alright. Okay, so now we'll do a question to better understand this principle of kinetic and static friction. So please read through this question first and then I'll explain. Okay, so let me read this out. So you have a block of mass 1 kg placed over a rough surface and a horizontal force F is applied on the block. We have to find out the values of the force of friction F and the acceleration of the block if the force takes different values 0 to 4, 5, 6 and 8 newtons, and the coefficient of static friction is given to you as mu 0.5 and 0.4 is the coefficient of kinetic friction, G we take as 10, right? Now to solve for this, first we have to find these two values, FL and FK. FL is the limiting friction. Limiting friction means the maximum value of the static friction. Fk is the kinetic friction. So if I use the formula for Fl, that is equal to mu s times the normal reaction. Normal reaction in this case is just mg. So mu s is given to you in the question as 0.5, mass is 1 and g is 10. So we get 5 newtons. So this is Fl, the limiting friction. Now we find Fk, that will be equal to mu k times the normal reaction, mu k times mg. Mu k is given to you as 0.4, mass is 1, g is 10. So we get 4 newtons. This is the value of kinetic friction. So as you can see, this limiting friction is always greater when you are comparing it with kinetic friction. Now these two values we will require to now solve the question. Okay. So here what I have done is, so we will solve for this question depending on forces. In the first case, the applied force is 0 newtons. This means if the applied force is 0, the friction will be automatically be 0 because there is no need of a friction. So net force in this case is 0, so there is no acceleration. So the free body diagram for this is simple. So we have a capital F which is equal to 0 on this side and friction which is also 0. This was easy. Now let's say the force is 2 newtons. Now we have to first check what is the maximum value of the static friction which is possible. In the previous slide we had seen that this value was 5 newtons and kinetic value was 4 newtons. Now this 2 is actually less than the maximum possible value, which means the friction will be equal to the applied force. Friction will be 2 newtons. Consequently we say that the net force is 0 and hence the block's acceleration is 0. In the free body diagram there will be a force of 2 newtons to the right and a friction of 2 newtons to the left. Now in case of 4 newtons as well, which is the applied force, the friction in this case is equal to the applied force. Now as you can see that friction is self-adjusting depending on the applied force. So in this case same thing happens, acceleration and force are 0, and the free body diagram for this will be 4 newtons to the right and 4 newtons to the left, which is the friction. Now till here it was easy because the body is at rest. Now the next force is 5 newtons. So the force is F. Now the maximum value we saw was 5 newtons. So in this case friction will exactly balance that out. So even in this case the net force is 0, acceleration is 0, and the free body diagram remains the same. But now things will start to happen when the force exceeds the limiting value 6. Then now actually what you have to observe is the force has crossed the threshold of 5 newtons, which means the body is now moving. So body starts to move. So the friction in this case, the friction applied in this case will be the kinetic friction, and we had seen that that value was 4 newtons. Now after this, whatever happens to the force, if we keep on increasing the force, the value of friction is a constant. It won't exceed the 4 newton. So friction in this case is 4. So the net force will be 6 minus 4, which is 2 newtons, and acceleration in this case would be the force divided by mass. So 2 by 1 is 2 meters per second square. So the free body diagram for this will be capital F, which is 6, and an applied force of 4 newtons. Alright, and let's take a last example when the force was 8 newtons. Even in this case, as I said, now the friction will always remain constant. So the difference of these two is 4 newtons, which is the net force, which will give you the acceleration of 4 meters per second square. So drawing the free body diagram, F is equal to 8 pointing rightwards and friction is 4 to the left, such that you have an acceleration of 4. In this case the acceleration was 2, right? Now so this was a bit tricky. So did you understand, both of you?
Yes, sir.
So please write all of this down. Let me.
So can you go to the first slide? Yeah, this.
So I wanted to ask something.
Yes.
In the free body diagram, do we not include the mg and n?
Yes, we do. But in this particular case, since the surface is horizontal, the n and mg actually balance each other out, right? So
Yes.
doesn't really matter. But in any case, you are right. If we are drawing the free body diagram, we have to incorporate the mg and n. But here, as I said, n and mg balance each other out. So, and anyways, the body is moving horizontally. So
Okay.
this is just for explanation's sake, but if you are drawing the FBD, you have to consider all the forces.
Yes, sir, done. Can you switch to the, yeah,
Okay.
some.
So in each case, the limit in friction keeps on increasing until it reaches the maximum point,
No,
right?
no. The value of static friction increases until it
Yeah, yeah,
reaches the
static
limiting
friction. Yeah,
factor.
static friction.
Yes.
Yeah, done, Sam. I'm done with all of the notes.
Okay, great. So, Smera, let me know whenever you finish.
Yes, sir, I can switch to the next slide.
Okay.
Yes, sir, I'm done with it.
All right.
Great.
Now let's move on. So now what we will do is now we'll observe graphically the effects of these friction in the same example.